All right, we're back for the second part of our Chapter 11 content that's being presented in the videos that you're watching in outside of class time, I should say, to get us ready to finish Chapter 11. So we've already discussed intermolecular forces, and now another major topic in this chapter is the different phases of matter and how their behaviors are described and what we know about them. But we've already looked at gases back in Chapter 5. We learned a great deal about the behavior of gases, and so we don't need to spend too much energy and time on them in this chapter. And we'll focus a little bit on liquids and solids, and in this segment of the video I'll be talking about liquids, and then once we're back into lecture class time, we'll use some of that time to talk about solids as we round out this chapter. All right. So for liquids, we want a little bit of a mental image of what a liquid is. Remember that these are now molecules that are touching one another in the sample of molecules that would make up a liquid. But the molecules have freedom to move around, and they can be at any position throughout that collection of molecules. As opposed to a gas where the molecules are not touching each other at all, and they can be anywhere in the volume of their vessel. And then a solid, the molecules are touching each other, but they don't get to change positions. Each molecule has a position, and all that the molecule can do is vibrate back and forth. All right? So liquids are kind of a mix, a hybrid, if you want, between what's happening in the solid and the gas phase. We don't have as many equations to describe the behavior of liquids like we do for gases. But one of the major things that we know about liquids is that liquids undergo a process that we call vaporization. You might commonly use the word evaporation to talk about, that's the word you've probably heard for what I'm describing right here. So liquids experience this vaporization. That's the conversion of liquid to gas. All right. Now, this happens at all temperatures, and so we want to distinguish vaporization from other processes like boiling, which we'll definitely get a chance to talk about today as well. So it happens at all temperatures, not just at the boiling point, right? I'm sure you've all seen a puddle of water on the street or a sidewalk after a day when it's rained, and then that puddle disappears, right? It's evaporated. Well, now we want to use the more scientifically correct term that it has vaporized. And regardless of what that temperature is on any given day, that puddle would still be able to vaporize and convert to the gas phase. Right? So this vaporization occurs at all temperatures. And what's interesting about vaporization, if we confine a liquid in an enclosed container, so this would be our liquid. When the liquid vaporizes, it's going to generate pressure because it generates a gas. And therefore, it's going to cause pressure. And given some time, what we'll see is that early on in this process, the vaporization will win out, and we'll have lots of vaporization. But as we start to build up the supply of gas particles up here in the headspace above this liquid, then we will start to see condensation beginning to occur. So we might still have a lot of vaporization, but now we'll start to have some condensation, returning of the vapor back into the gas phase where the molecules get caught. And eventually, these two processes will become equal to each other. So when the amount of vaporizing equals the amount of condensation that's occurring, this is what we would term vapor-liquid equilibrium. Okay? So when the two processes are both occurring at the same speed, we have a condition of equilibrium taking place. And what that's going to mean for the gas that we've generated, so going from one picture to the next, the amount of gas is going to be increasing, and then it's finally going to reach a steady state amount. If you were to draw a graph, this pressure would have, over time, built up, and then it would have steadied out. This constant amount of pressure that we see, that we would have in this final picture here, the amount of gas particles that we have, and thus the pressure, is what we call the vapor pressure. All right, and the vapor pressure of a liquid, okay, is highly dependent upon the temperature, the type of intermolecular force that might be present, all right? And then those are the two main factors, but you might also consider the molar mass of the liquid, all right? So how heavy the molecules are, all right? So these are three variables that dictate the vapor pressure that can be generated by any given liquid. So what I'm getting at is that two different substances placed side by side, all right, in containers, liquid A and liquid B, these could be at the same temperature, same size container, but they will generate different amounts of pressure up above their liquid based on what we've talked about earlier in this chapter, the type of intermolecular force of attraction. Here I've tried to draw a lot more particles of A in the gas phase. So we have a higher vapor pressure over here for A. The conclusion that we can draw from that is that A must have a weaker intermolecular force, because the intermolecular force being lower or weaker is what allows us to pull more molecules out of that liquid phase. Over here in liquid B, the stronger intermolecular force would hold those molecules down together in the liquid phase. All right? For many liquids, we've already characterized this behavior very well. We've studied a lot of them, and we have what are called vapor pressure curves. So we could just go to a resource textbook, a resource book, or the internet, and we can find a drawing, a curve, a diagram that will show us the pressure, the vapor pressure, at all of the possible different temperatures. All right? And these curves always look something like this. All right? And so if this was the curve for substance A that we just had, all right, the curve for substance B, I can already conclude, would come in underneath it, would have a slightly different trajectory, so to speak, to it. They're always exponential in shape like this, in that the vapor pressure is always increasing as the temperature increases. That never changes. Vapor pressure always goes up as temperature goes up. All right? But these two curves shown side by side reinforce the same thing that I explained with the pictures over here. At any given temperature, so if we just pick some temperature, the pressure of A, we can see, is greater than the pressure of B. Just what the picture shows as well. And that tells us again that the weaker intermolecular force exists in substance A. Also, we can see from this type of a comparison that at any given, to achieve any given pressure, we have to take B to a higher temperature. Meaning, again, there's a stronger force holding the molecules of B together to one another, so we have to add more energy to pull them apart to try to make the same amount. So if I wanted to get as many gas particles up here in the B liquid as I have in the A liquid, I would have to raise the temperature of B to a higher value. That's what this going sideways shows us. Okay? These vapor pressure curves also tell us something really interesting that might you might find fun to talk about for a few minutes. Okay. So if I consider the vapor pressure curve of any old liquid, and I'll put some numbers in there in a minute, I want to ask the question, what is boiling? So you're not here to answer this question for me in person, but when I usually ask the question, what is boiling? What do you see? What do you visualize when I say, what's a liquid boiling look like to you? We get answers like you see the bubbles coming up in a pot, right? If you're boiling a liquid in it, all right? We get answers like adding heat to change a liquid to a gas. All right, so those are fine, but let's break this down and think a little bit more about scientifically, chemically, what's happening. All right, in this term boiling that we have. First of all, what are the bubbles? When a liquid is boiling and you see those bubbles coming up out of a pot of water, for example, the most common liquid that you've probably boiled, what's inside those bubbles as they rise up to the surface of the liquid? All right? The answer is water. It is water molecules that have gone to the gas phase and that they have changed over to the gas phase, and then they've kind of collected together into an aggregate bubble that is less dense than the liquid water, and so they rise up to the top. And that's one of the real differences between boiling versus vaporization. In boiling, it occurs throughout the entire volume. Whereas vaporization occurs only at the surface. The only molecules in these cases that I've drawn over here that are capable of freeing themselves and getting into the gas phase are the ones that are at the surface. But when we reach the boiling point, we've added enough energy that now all the molecules throughout the sample are capable of breaking free of the attractive forces that they feel to other molecules and liberating themselves into the gas phase. All right? That's one of the signature differences. All right? The other interesting thing about boiling point is boiling point, the real definition of boiling point is the temperature at which a substance's vapor pressure equals its prevailing atmospheric pressure, equals the prevailing atmospheric pressure. Think of the atmospheric pressure as what's pushing down on the liquid, and the vapor pressure is what's being pushed out, right? So these cases that I've drawn here, imagine taking the pot lid off, or the container's lid off. Normally all these particles would then just escape as this liquid vaporizes, right? But when this liquid is pushing out as many particles as the atmosphere pushes back down with, all right, when these two numbers are equal, that is going to be the boiling point of our material. And so it's a little bit deceptive. If I were to ask you what's the boiling point of water, the most common answer that jumps to mind is 100 degrees Celsius. Well, the reason we're used to thinking that water boils at 100 degrees Celsius is on the water vapor pressure curve, 100 degrees Celsius corresponds to 1 atmosphere of pressure, normal atmospheric pressure. And so yes, we do say that the normal which implies that pressure equals 1 atm. The normal boiling point of water equals 100 degrees Celsius. But we can actually cause water to boil at any temperature that we want. If we were to put a lid on a sample of water and lower the vapor pressure, or lower the atmospheric pressure on that material, we could get water to boil at a temperature below 100 degrees Celsius. All right? This happens all the time, actually. If we go to higher elevations in the United States or other places around the world, the atmospheric pressure, even in Colorado, is lower than at sea level, and water boils at about 95 degrees Celsius at those altitudes. If you were to go all the way up to the summit of Mount Everest or the altitudes near that, the pressure is so low that water will boil at 72 degrees Celsius. Right? Now, it is boiling. It is pushing out the same amount of pressure as what the atmosphere is pushing back down on it at those conditions. It's not as hot though. And this is why sometimes if you buy like a box cake mix or brownies, you might see high altitude cooking instructions on that. Or even on pasta sometimes you see these instructions for cooking a product at a higher altitude. Because if you're boiling spaghetti in water that's only 95 degrees Celsius when it's boiling, it's going to take longer to cook it. If you're baking a cake that has some liquid in it that is doing the cooking of the eggs and other stuff that's in there, it's going to take longer to deliver as much energy at a lower temperature. All right? If you're going to cook rice when you're near Mount Everest, it's going to take hours for that rice to get soft at a lower temperature like 72 degrees Celsius. I could boil water in this room right now if I hooked it up to a vacuum pump that drew the supposed pressure that's over top of the water so far down so that it matched the pressure that the water is pushing out at 20 degrees Celsius, roughly the room temperature that we're in. It would be totally useless for cooking, but it would look exactly the same as water boiling in a pot on your stove at home. You would see those bubbles because you would be having the rapid conversion of the liquid to the gas phase because all of the molecules would be capable of breaking free of their intermolecular forces. But it would, we have to discontinue this notion that boiling is heating a substance to turn it into a gas. Boiling is simply the condition when the amount of pressure being generated by the liquid equals the pressure that's being applied externally upon that liquid. All right? So that's one neat thing when we talk about boiling. Now, these curves, before I erase it here, these curves, as I mentioned, all have an exponential shape to them. And we can model what this pressure is as a function of this temperature. And that would allow us to predict other properties of liquid materials. And so one of the common ones that we're interested in, and we're going to be doing some laboratory experiments on it next week, actually 2 lab experiments on this, is the amount of energy that it takes to vaporize this substance, right? So I don't have the 2 curves up here now earlier, but I spoke about the different intermolecular forces of attraction that A and B, my 2 example liquids earlier, would have. Well, the stronger something's intermolecular force of attraction is, the more likely it is that it requires more energy to vaporize that. And that energy to vaporize a mole of a liquid is called the enthalpy of vaporization. And this relationship to vapor pressure was first determined, I believe, by 2 different scientists, and that's why the equation shares both of their names. And it's called the ClausiusClapeyron Equation. The Clausius-Clapeyron equation says that the natural logarithm of the vapor pressure of a liquid is equal to negative enthalpy of vaporization, delta H VAP, divided by RT plus some constant then. And it's written in this form so that it takes that curved structure that I just showed you a little bit ago and turns it into a straight line. But now you'd have to graph the ln of the pressure versus 1 over the temperature. And that turns that curved shape that went up now into a straight line that comes down. All right? And we'll get to why we'd want to do that in just a minute. Okay? So some of the terms that we have here, again, delta H VAP. This is what we're calling the enthalpy. So that's an energy we know of vaporization. The amount of energy it takes to vaporize 1 mole of a liquid. R is our universal gas constant, but when we see it in this context, we're going to use a different set of units. 8.314 joules per mole Kelvin, as opposed to the 0.08206 atmosphere liters per mole Kelvin that we used in the ideal gas law. It really is the same number, it's just expressed in a different set of units. Like taking a $100 bill to a bank and say, I'm going to country X, can you change this into their currency? And they might give you 375, whatever they call their currency. It's the same value, just expressed now in a different set of units. All right? And we need to use those units here because this enthalpy of vaporization is something that would be in joules per mole. So we're going to want matching up of those values. And of course, T is going to be the temperature in Kelvin. All right? These P's are the enthalpy, the vapor pressures that we would have. Okay? Now the reason we would express this relationship this way as opposed to its exponential form, P equals E raised to some exponent, that would be the equation that predicted the shape that we saw earlier on the vapor pressure curves. The reason we've manipulated it into this fashion is that if we were to do an experiment in the lab and collect several vapor pressures at different temperatures, several P-T combinations, and then plot them in this form, this straight line, y equals mx plus b, is the form that all straight lines have. And we can relate these two to one another. Okay? The b, the least important part here, the constant would be b. Okay? Our graph's y is ln of pressure. So that's our y. And then our graph's x is 1 over temperature that we see right here. It's in the denominator, which leaves the slope of this graph to be the negative delta H VAP divided by R. And this is what we'll be doing in lab next week. We'll collect vapor pressures at different temperatures for some materials, and we'll be trying to determine delta H vaporization, the enthalpy of vaporization. Okay? We can also then actually use that sort of data to predict the boiling point of a substance. So when we have a whole bunch of data points, a graph might be very useful. But for 2 data points, because 2 data points is all it takes to make a line, right? You only need 2 points to make a line. So the 2-point version of this Clausius-Clapeyron equation would have ln of P2 divided by P1 equaling the negative delta H vaporization over R times 1 over T2 minus 1 over T1. And the constant disappears in that case. It's just, it would be subtracted out, actually. All right? So you can use this equation as well to predict a number of things. If you know one pressure-temperature combination, a P1 and a T1, you can predict the vapor pressure at a different temperature. Or you can predict the temperature required to have a certain vapor pressure that you might be after. That's how we can get the boiling point of a substance. By measuring one pressure-temperature combination, we can figure out what temperature do we need to get atmospheric pressure, our second pressure, because that's when boiling would occur. All right? So let me do an example of how we're going to make use of this type of calculation. The enthalpy of vaporization, the delta HVAP of carbon tetrachloride, CCl4, is 29.8 kilojoules per mole. All right? Its normal boiling point is 76.8 degrees Celsius. Okay? What is its boiling point at 0.5 atmospheres? So if we decrease the atmospheric pressure on a sample of carbon tetrachloride to half an atmosphere, what temperature will allow it to boil is the question that we're after here. All right? So we can use the Clausius-Clapeyron equation to answer this question. And our first combination that we have a P1-T1 combination. It's kind of hidden, but when we say normal boiling point, remember, that implies 1 atmosphere of pressure. And then we have our 76.8 degrees Celsius, which would be a temperature of 349.95 Kelvin. So these can be our P1 and our T1. And then P2, T2, we know P2, we're defining it as half an atmosphere, but we're not sure about T2. So what temperature would go with this atmospheric pressure to allow this carbon tet to boil? So now it's a matter of doing the algebra to try to solve for T2. Okay? So we can begin with ln of P2, 0.5, divided by 1. That's going to equal negative. Now I'm going to put my R in first, 8.314 joules per mole Kelvin. And when I did that, I did it intentionally because this enthalpy now needs to be 29,800 joules per mole. Right? The kilojoules needed to be converted to joules to match up down here. Okay? And then we have 1 over our unknown T2 minus 1 over 349.95 Kelvin. So now it just becomes numbers. This I can calculate the ln of 1/2 is going to be negative 0.69315, it looks like, equals, this becomes negative 3,584 times your 1 over T2 minus 1 over 349.95. So I'll need to distribute, okay? So I've got negative 3,500, that's actually 3,584.3 over T2 plus negative times the negative 10.2424 when I take the 3584 divided by 349. All right? This still equals the negative 0.69315. You're going to add or subtract this to the other side. So you have negative 10.9355 on the left side equals your negative 3584.3 over T2. So T2 is going to equal, your two negatives become positive, 3584.3 divided by the 10.9355. Quick check before I do my answer, thinking about this problem. Boiling point always decreases with atmospheric pressure. That's what we saw with the case of water. It would increase with higher atmospheric pressures. I didn't talk about it, but that would be what's called a pressure cooker. If you've ever heard of one of those, you can make water stay as a liquid to a higher temperature, but don't want to get too off track. I'm just thinking about that right now because our 1/2 atmosphere is lower than our normal Okay, I was pretty close to finishing. Sorry about that. The video shut off. We're literally just a few seconds away from it. All right. So we can sort of guesstimate and understand that because we're at a lower atmospheric pressure, 1/2 than normal, our boiling point better be less than the original 76.8. So the Kelvin boiling point is 327.77 Kelvin. That is less than 349, so far so good. And if I turn that backwards into the degrees Celsius, it is only 54.6 degrees Celsius.